We're going to start chapter 4 with section 4.2, which is about mathematical induction. And what mathematical induction is used for most of the time is taking a set of propositions which hold true for different countable values like 1, 2, 3, 4, and so forth. So that's what we have here. It says principle of mathematical induction. It says let P of m, P of n plus 1, and so forth be a sequence of propositions. So we go about proving a sequence of propositions by mathematical induction by starting out verifying that P of m is true, and then assuming that P of k is true, and showing that it is then true for P of k plus 1. If you look at this picture of dominoes over here, it's meant to kind of illustrate the idea behind mathematical induction. If the first domino falls, it's going to knock the next domino over. And if all the dominoes fall and we assume that they fall all the way up to some domino up ahead, and if we can show that that domino will keep knocking over the one next to it, then we'll figure out that the dominoes will all fall all the way down the line. Here's another statement that includes a little bit more verbiage to it. Method of proof by mathematical induction. And so let's think of it this way. It says consider a statement of the form for all integers greater than or equal to a, property P of n is true. We've proved this by mathematical induction in 2 steps. This way it says the basis step is step 1. That's what they call B up here above. And we start off with A, or whatever the very first number is, and show that it is true for that number. So after we do the basis step, we proceed to step 2, which is called the inductive step. In the inductive step, we follow this kind of structure here. We suppose that P of k is true, where k is any particular but arbitrarily chosen integer greater than or equal to a. Sometimes they refer to this as the inductive hypothesis. Then, following from that assumption, we have to show that P of k plus 1 is true. So these are sort of the key steps. Basis step, then the inductive step where we suppose it's true, and then show it's true for the next following integer k plus 1. So let me show you our first example of proof by mathematical induction. It says for each positive integer n, let P of n, our proposition to be proven, be n factorial is greater than 2 to the n power. And we want to claim this is true for n greater than or equal to 4. Okay, so the first thing I do is the basis step, or the base step as sometimes I call it. The basis step is to start with the first number that it says greater than or equal to 4. So we're going to show it's true for n equal to 4. We have to start with the base number here. So for n equal to 4, 4 factorial is 1 times 2 times 3 times 4, and that's equal to 24, which is greater than 16, or 2 to the 4th power. So for the base step, we can see that 4 factorial is greater than 2 to the 4th. So it holds true in that step. The next part is the inductive step. Okay, for the inductive step, we're going to assume that it's true for k. Assume k factorial is greater than 2 to the k power for k greater than or equal to 4. Now, once we assume that it's true for k, we have to show that it's also true for k plus 1. And by that I mean we have to show that k plus 1 factorial is greater than 2 to the k plus 1. So what we'll do here is for n equals k plus 1, we'll have k plus 1 factorial equal to k factorial times k plus 1. We can write it this way since it's multiplied all the way up to k plus 1. So we'll just pull off the k plus 1 and leave k factorial. And we know that that has to be greater than 2 to the k times k plus 1. And the reason why we can say that it's greater than that is we assumed that k factorial is greater than 2k. 2 to the k, I should say. So we see here k factorial, it's greater than 2 to the k power. So we can make that assumption here for greater than. So we know this is greater than or equal to 2 to the k times 2. And the reason why we can say that is we know that k plus 1 is starting from 4. So it'd be the number k starts from 4, so it's definitely bigger than 2. So we can put 2 there in its place and say it's greater than. But this 2 times 2k to the k power is the same thing as 2 to the k plus 1 power. So what we just started out here was with k plus 1. We now have that it's greater than 2 to the k plus 1. So we can say then that k plus 1 factorial is greater than 2 to the k plus 1. And by mathematical induction, we can then say that n factorial is greater than 2 to the n for all n greater than or equal to 4. Now in my next one, I'd like to show that 1 plus 2 plus all the way up to n is equal to n times n plus 1 over 2 for all n in the positive integer set. We're going to do this by induction, so the first thing we do is the basis step. For the basis step, we start with the first number for n. So we have to show for n equals 1. Since n equals 1 for the first number in positive integers, so for n equals 1, our summation would just equal 1, and that's equal to, the formula would go 1 times 1 plus 1 over 2. That's equal to 2 over 2, and so we see that indeed it's equal to 1. So it checks out here. Now for the inductive step, again, like last time, we assume it's true for k. So we assume for n equals k, k greater than or equal to 1, that our thing we wish to prove, 1 plus 2 plus ... all the way up to k, is actually equal to the formula k times k plus 1 over 2. So next thing we want to do is make this work for k plus 1. For n equals k plus 1, our sum 1 plus 2 plus ... plus k will now go up to plus k plus 1. So one additional number added to the end. But we did make an assumption about everything up to k being added together. We say up above that that's all equal to k times k plus 1 all over 2. And then that's plus k plus 1. Now what we can do is just manipulate it with algebra at this point. We can get a common denominator, add them together. It would look something like k squared plus k plus 2k plus 2, all divided by 2. Okie doke, that's going to turn into k squared plus 3k plus 2 divided by 2. Again, my goal here is to make it look like the formula, but fit it with k plus 1. So this is going to be equal to, I'm going to factor the top as k plus 1 times k plus 2 all over 2. And now the cool thing here is that k plus 2, why don't we go ahead and rewrite that as k plus 1 plus 1. And so now we check to see, does this fit what we would expect the formula to look like if it had a k plus 1 substituted in for it? Well, looking up above at the formula we had for k, that's just for k. Now we have a k plus 1 and a k plus 1. So it does fit in with what we would expect to see when k has been replaced with k plus 1. So now we have the formula verified by math induction. So we can then say, thus 1 plus 2 plus ... plus n is equal to n times n plus 1 over 2 for n in the positive integers by math induction. Now we're going to look at this one here that we want to prove the geometric sequence formula. The summation I equals 1 to n of r to the I is equal to r to the n plus 1 minus 1 all over r minus 1. For r not equal to 0, r not equal to 1, and n in the natural number set. So here's what we're going to do first. We're dealing with n primarily. That's our primary concern here to prove this by induction. So we need to start with our basis step. We need to start with the first number for n. Since we're dealing with n is in the natural number set, I'm going to say for n equal to 0. So for n equal to 0, the summation I equals 0 to 0 of r to the I is equal to r to the 0, which is equal to 1. And the other side of things, the other side of this formula we want to verify it for, if we plug in 0, r to the 0 plus 1 minus 1 over r minus 1 would be equal to r minus 1 divided by r minus 1, which is just equal to 1. So we show that the two sides here are equal for n equal to 0. So next thing we do is the inductive step. So now we're going to assume for k, assume for n equal to k, in this case k is greater than or equal to 0, that our formula, summation I equals 0 to k, r to the I is equal to r to the k plus 1 minus 1 all over r minus 1. So now we have to show that this works for k plus 1. So for n equals k plus 1, we're going to be looking now at the summation I equals 0 to k plus 1 of r to the I. So we can rewrite this as the summation I equals 0 to k of r to the I plus r to the k plus 1. And so what I've done here is I've split off the r to the k plus 1 term out of the summation. By our assumption above, this summation is equal to r to the k plus 1 minus 1 all over r minus 1 plus r to the k plus 1. So now we need to use some algebra here to try to combine these together. Getting a common denominator and so forth here, we can rewrite this as r to the k plus 1 minus 1 plus r to the k plus 2 minus r to the k plus 1 all over r minus 1. And simplifying this down, this will turn into r to the k plus 2 minus 1 all over r minus 1. And that's the same as r to the k plus 1 minus 1 over r minus 1. And we'll double check, is this in the same format as the formula, but with k plus 1? Indeed, if we go back to our assumption for k, it had k plus 1, and now we have k plus 1 there, plus 1. So it's the same thing, but with k plus 1. So this verifies for math by math induction. The summation I equals 1 to n of r to the I is equal to r to the n plus 1 minus 1 all over r minus 1 for n in the natural number set. Now this next one we're going to do is prove that 8 to the n minus 2 to the n is divisible by 6 for all n in the positive integers. So the first thing I'm going to do is the basis step, which is to verify for the first number for n. In this case for n equals 1. 8 to the 1 minus 2 to the 1 is equal to 6. So that verifies that it's true for n equals 1. And then for the inductive step, what we'll do is assume for n equal to k greater than or equal to 1, that it's divisible by 6. 6 divides 8 to the k minus 2 to the k. So this also can be said as meaning that 8 to the k minus 2 to the k equals 6p for some integer, or in this case just natural number p. Our next step is to follow along here and to prove that this is true for k plus 1. So for n equals k plus 1, we'll have 8 to the k plus 1 minus 2 to the k plus 1. If we can verify that this is also divisible by 6, then we will have proven the proposition. So I'm going to use some manipulation on this here. Now rewrite this as 8 to the k plus 1, and then in the middle I'm going to put a minus 8 times 2k and a plus 8 times 2k. I'm adding and subtracting the same thing, not changing anything by doing that, but I'm adding some extra things that I might be able to factor and manipulate here. So sometimes we do that. Sometimes we have to add and subtract the same thing in order to make things go in the right direction. So by doing what I've done here, I've put an 8 that can be factored with another 8 here in the front. So we're going to change this into 8 times 8 to the k minus 2 to the k plus 8 times 2k minus, we're going to write the last part as 2 times 2 to the k. So that now that matches up with the 2 to the k here, and we have another 2 to the k. They're like terms now, basically. So we're going to write this as 8 times something. That something we have in parentheses here, we know that that's a multiple of 6 by what we assumed up above. So we could put 6p there in its place. And then over here, this would reduce to 6 times 2 to the k. I'm getting 6 by taking 8 minus 2 times 2 to the k. And now, can we say that this is divisible by 6? Now, each term is a factor of 6 divisible by 6. And so we can say 6 divides 8 to the k plus 1 minus 2 to the k plus 1. And so by math induction, 8 to the n minus 2 to the n is divisible by 6 for all n in the natural or in the positive numbers. And this next one, we're going to take 37 to the 500 power minus 37 to the 100 power and show that it's a multiple of 5. What we're going to do here is actually write this in a certain form and then prove it for that. So rewriting this thing as 37 to the 100 raised to the fifth minus 37 to the 100, we could write this in the form of n to the fifth minus n. And so we're going to prove that this is true for n, and then it will follow it's true for those numbers we have specifically here. So we're going to prove n to the fifth minus n is a multiple of 5 for n in the positive integers. So to do that, we'll use induction. We'll start off with our base case or basis step here. So we'll start with n equals 1. For n equals 1, 1 to the fifth minus 1 is equal to 0. And that's a multiple of 5. So now we'll follow to the inductive step, which means we have to assume it's true for n equals k. So assume for n equals k, k is greater than or equal to 1, that k to the fifth minus k is a multiple of 5. That is, we can then say that k to the fifth minus k is equal to 5p for some positive integer p. This is a multiple of 5. So now we have to prove that it's true for k plus 1. Then for n equals k plus 1, k plus 1 raised to the fifth minus k plus 1. Well, we'll have to expand the binomial out here. If I expand k plus 1 to the fifth, I get k to the fifth plus 5k to the fourth plus 10k to the third plus 10k squared plus 5k plus 1. That's minus k and then minus 1. I can rewrite this as k to the fifth minus k. So I'll move the minus k up there to the front. And then everything else left over here can get to a multiple of 5. And so we'll be able to write this as plus 5 times k to the fourth plus 2k to the third plus 2k squared plus k. And so now we see everything here is a multiple of 5. This is a multiple of 5. This is a multiple of 5. Or in other words, we could write it as 5p plus 5 times k to the fourth plus 2k cubed plus 2k squared plus k. So for n equals k plus 1, it's a multiple of 5. So we can say by math induction, n to the fifth minus n is a multiple of 5 for n in the positive numbers. And then it follows that the number we started with, the 37 raised to the 500 minus 37 to the 100, since it fits this form, it's also going to be a multiple of 5. So for this next one, it says for all integers greater than or equal to 3, 2n plus 1 is less than 2 to the n power. So this follows along the same kind of process as before. We start with our basis step. And so in this case, we have to start with n equals 3. So check that is true for n equals 3. 2 times 3 plus 1 is equal to 7. And that's less than 8, which is the same as 2 to the third power. So it checks out to be true here for the first number, n equals 3. So now we'll follow into the inductive step. So as we've done before, I want to assume for n equal to k, k is going to go from greater than or equal to 3, that 2 times k plus 1 is less than 2 to the k. And then we have to continue from there for k plus 1, for n equals k plus 1. Can we make it work? Well, let's start with 2, and then we'll have k plus 1 plus 1. What are we trying to show here? Again, we want to show that 2k plus 1 is less than 2 to the k plus 1. That's our goal. So let's see if we can do that. So let's see, this is going to be equal to 2k plus 1 plus 2. And I write it like this because I can say that 2k plus 1 is less than 2 to the k, since that's what we assumed up above for k. So this would look like less than 2 to the k plus 2. Now, this is actually less than 2 to the k times 2, which would make sense, right? Since multiplying would give us a bigger number than adding by 2. And since also k is greater than or equal to 3. So for sure, we're getting bigger numbers by multiplying by 2. But this thing is the same thing as 2 raised to the k plus 1 power. So following rewriting it, I can now say that this thing I started with is less than this thing, 2 to the k plus 1. So we can say 2k plus 1 is less than 2 to the k plus 1. And that shows by math induction that our original thing is true. So thus, by math induction, 2n plus 1 is less than 2 to the n for n greater than or equal to 3. Okay, now the last one in this section is going to be a little bit more abstract. We're going to prove that the number of elements in the power set of a set S, and that's a finite set, not an infinite set, is 2 to the n power. So how we're going to do this, we're going to start out by saying let n equal the number of elements in set S. Sometimes this is denoted bar S is equal to n. Sometimes they put bars around it to denote the number of elements in the set. We haven't had a really use for that notation, but it sometimes shows up. So what we need to do first is the basis step here. So what we need to do is start with n is 0. For n equal to 0, the number of elements in the set is 0, and thus S must be the empty set. Thus, as a result, the power set of S is just simply the empty set, or the set containing the empty set, has just one element, which is the same as 2 to the 0 power. So it holds true for a set which is empty. An empty set has a power set with only one thing, which is just the empty set. And that's the same as 2 to the 0 power. Now for the inductive step, okay, we need to assume this is true for n equals k. So we say assume for n equals k, k greater than or equal to 0, that the power set of S has 2 to the k elements. Let's say we can write them out as S is equal to element 1, element 2, all the way up to the last element, k. So let's say it has this look to it so far. Okay, and then for n equals k plus 1, our set S is going to look like element 1, element 2, all the way up to element k, and then element k plus 1. One more element added to the end. Okay, so let's let T be equal to the first k elements. Then by our assumption, the power set of T has 2 to the k elements. Also, the power set of T is the same as the power set of S, except for the subsets containing k plus 1. Okay, now the next thing to be able to recognize is since there are 2 to the k elements in the power set of T, the power set of S contains 2 to the k more elements made from the subsets in the power set of T, but with the element k plus 1 included. Thus, the power set of S has 2 to the k plus 2 to the k, which is equal to 2 times 2 to the k, or 2 to the k plus 1 elements. Hence, we verified that for k plus 1, we'll get 2 to the k plus 1 elements. And so we can say by math induction, the power set of S has 2 to the n elements for a set S having n elements.